Good day, sir. This is Carly Cebuano, Thermodynamics 1, Module 4. This module discuss about the Charles law, Boyle's law, and Gay-Lussac's law. So first is Charles law. Charles law. Volume of gas varies directly with the absolute temperature at a constant pressure. Volume equals to Kelvin temperature. Formula is V1 over T1 equals to V2 over T2 by Jacques Alexandre Charles, mathematician, physicist, inventor, Montgency, France, November 12, 1746 to April 7, 1823. Charles law. Formula equals volume 1 over temperature 1 equals to volume 2 over temperature 2. So as we have seen in sample, heat and cold. So in heat, when the temperature is high, the volume also is high but remains constant the temperature. In cold, the temperature is low, then the volume is low also, but the pressure is remain. Here is the three problems of Charles law. Problem number 1. A 200 ml of air at 20 Kelvin is heated to 40 Kelvin. What is its new volume? So, since the volume 1 equals given 200 ml, then the temperature 1 equals to 20 Kelvin. Also, the temperature 2 equals to 40 Kelvin. So, what is its new volume? So, the volume 2 is the missing. So, by getting the answer of volume 2, you need to use the formula of Charles law. B1 times T1 equals to V2 times T2. So since the V1 is given 200 ml times T1 20 Kelvin equals to the missing V2, then the value of T2 40 Kelvin, then shift solve. So 200 times 20 equal alpha x, so alpha x times 40k. So shift solve. So the value of volume 2 equals to 100 ml. Final answer. So let's proceed to problem number 2. So problem number 2. What will be the volume of a gas sample at 355 Kelvin if its volume at 273 K is 8.57 liters? So since the temperature 1 was given 355 Kelvin, then its temperature 2 equals to 273 Kelvin, then the value of V1 equals to 8.8757 liters. Then you need to find also the V2 or volume 2. So missing is volume 2. So by getting the answer of volume 2, you need to use the formula of V1 over T1 equals to V2 over T2. By equating that, since V2 is the missing, we need to equate the formula by V2 equals to V1 T2 over T1. So let's proceed. V2 equals to the value of V1 equals to 8.57 liters times the value of T2 273 Kelvin over the value of T1 357 or 355 Kelvin. So V2 equals to, shift solve, so alpha equals 857 times 273 over 355. So shift solve, the value is 6 point, answer is 11.1 liters. So that's the final answer of volume 2. Then proceed to problem number 3. So problem number 3. A balloon full of air has a volume of 2.75 liters at a temperature of 18 degrees Celsius. What is the balloon's volume at 45 degree? So since the volume 1 was given equals to 2.75 liters, then the temperature 1 equals to 18 degree. Also the value of temperature 2 equals to 45 degrees Celsius. So by equating the temperature into Kelvin, we need to add 273. So equals to 18 plus 273, 291 Kelvin. Then the temperature also plus 273 equals to 45 plus 273, 318 Kelvin. Then volume 2 is missing or unknown. So by getting that, we need to use the formula of V1 over T1 equals to V2 over T2. So let's proceed to the value of V1, 2.75 liters over the value of T1, 291 Kelvin equals to the unknown or V2. Then the value of T2 equals to 318 Kelvin. So let's solve. Calculate 2.75 over 291. So alpha equals alpha x over 218. So shift solve. So the final answer is 2. Volume 2 equals to 2.060 liters. Cancel the Kelvin. So V2 2.06 liters. Boyle's law. Pressure and volume are inversely related at a constant temperature. So pressure times volume equals to Kelvin. As one goes up, the other goes down. So pressure 1 times V1 equals to pressure 2 times V2. The father of modern chemistry, Robert Boyle, chemist and natural philosopher, January 25, 1627, December 30, 1690. Boyle's law formula. Pressure 1 times volume 1 equals to pressure 2 times volume 2. As we can see in the example image, in increased pressure, when the pressure is increased, the volume is low and the temperature is remain constant. Also the decreased pressure, when the pressure is low, the volume is high and the temperature remains constant. Boyle's law problem number 1. The volume of air in the Marshmallows blaster is 450 ml. The pressure is 1.0 atm. If I decrease the volume to 50 ml, what will the new pressure be? So since the volume 1 is given equals to 450 ml, 450 ml. Then the pressure 1 equals to 1 atm. Then the volume 2 equals to 50 ml. So the missing here is a pressure 2, or the unknown. So by getting the value of pressure 2, you need to use the formula of Boyle's law. So P1 times volume 1 equals to pressure 2 times volume 2. So the value of P1, 1 atm, times the value of V1, 450 ml, equals to the unknown P2 times the value of V2, 50 ml. So so 1 m times 450 divided by x times 50. So the value of the P2 equals to 9.00 atm. Cancel the units of ml. So the final answer is 9 atm. So proceed to problem number 2. A sample of oxygen gas has a volume of 150 ml when its pressure is 0.947 atm. What will the volume of the gas be at a pressure of 0.987 atm if the temperature does not change? So since the value of volume 1 is given also, V1 equals to 150 ml, then the pressure 1 equals to 0.947 atm, then the value of the pressure 2 equals to 0.987 atm. So the unknown here is volume 2. We need to use the formula of Boyle's law. The P1 times V1 equals to P2 times V2. Since the V2 is unknown, we need to equate the formula for this type. So V2 equals to P1 times V1 over P2. So proceed to the value of P1, 0.947 atm, times the value of B1, 150 ml, over the value of P2, 0.987 atm. So calculate alpha x equals 0.947 times 150 over 0.987. So the value of the volume 2 is 1.43, 143, I mean 0.92, or V2 equals to 144 ml. Cancel the units of atm, so ml. So V2 equals to 142 ml. So proceed to problem number 3. So problem number 3. The pressure on 2.50 liters of anesthetic gas changed from 105 kPa to 40.5 kPa. What will be the new volume if the temperature remains constant? So given also the pressure 1 equals to 2.50 liters. Then the change from then the volume 1, then the pressure 1 equals to 105 kPa. Also the value of pressure 2 equals to 40.5 kPa. So the volume 2 is unknown. Volume 2 is unknown. So since the temperature is constant, you need to use the formula of Boyle's law. So formula of Boyle's law, P1 times V1 equals to P2 times V2. So equate also since the unknown is volume 2. So volume 2 equals to P1 V1 over P2. V2 equals the value of P1, 105 kPa times the value of V1. V1 equals to 2.50 liters over the value of V2, 40.5 kPa. So calculate. So alpha x equals 105 times 2.50 over 40.5. So the value of the V2 equals to 6.48 liters. Cancel the units. So the final value is 6.48 liters. So next is Gay-Lussac law. So at constant volume, pressure and absolute temperature are directly related. So pressure equals to temperature. Pressure 1 over temperature 1 equals to pressure 2 over temperature 2. By Joseph Louis Gay-Lussac, experimentalist, Limoges, France, December 6, 1778 to May 9, 1850. Gay-Lussac is the French chemist born in 1778, died in 1850, discovered the relationship between the pressure of a gas and its absolute temperature. Gay-Lussac laws state that the pressure of a given mass of a gas varies directly with the absolute temperature of the gas when the volume is kept constant. So, Gay-Lussac problem number 1. So, a gas has a pressure of 103 kPa at 25 degrees Celsius. What will the pressure be when the temperature reaches 928 degrees? So, since the pressure 1 was given, pressure 1 equals to 103 kPa. Then the temperature 1 is equals to 25 degree. Also the temperature 2 equals to 928 degrees Celsius. Then the unknown here is pressure 2. So since the temperature is degree, we need to add 273 to get the value in Kelvin, equals to 25 plus 273 equals to 298 Kelvin. Then the temperature to also plus 273 equals to 928 plus 273 equals to 1201 Kelvin. So need to use the formula of Gay-Lussac laws. So P1 over T1 equals to P2 over T2. So the value, since the value of P1 is given 103 kPa over the value of T1, 298 Kelvin, equals to the unknown P2 over the temperature 2. The given is 1201 Kelvin, so I need to use the solve. So 103 over 298 alpha 198 alpha equals alpha x over 1201. So shift solve. So the value of P2 equals to 415.1 kPe. Cancel the Kelvin. So the final answer is 415.1 kPe. So let's proceed to problem number 2. So problem number 2. So what would have been the initial temperature of a rigid container of a neon or Na at 1 atm if the final temperature was 293 Kelvin and the final pressure was 1.10 atm? So since the given the temperature 2 or final temperature was given 293 Kelvin, then the final pressure initial pressure is 1 atm. So 1 atm and the final pressure equals to 1.10 atm. So the missing here is, or unknown is, temperature 1. So by getting that, to use the formula of Gay-Lussac-Laws, the P1 over T1 equals to P2 over T2. So since the P1 has given 1.00 atm over the unknown temperature 1 equals to the pressure 2, 1.10 atm over the temperature 2, 293 K. So need to use the calculator. So 1 over alpha x alpha equals 1.10 over 293. So shift solve. The value of T1 equals to 266.36 K. Cancel down the ATM, then the initial temperature is 266.36 or 266 Kelvin. So let's proceed to problem number 3. So problem number 3. The gas left in a used aerosol can is at a pressure of 2.03 atm at 25 degrees Celsius. If this can is thrown onto a fire, what is the pressure of the gas when its temperature reaches 928 degrees? So since the pressure 1 is given, so pressure 1 equals to 2.03 atm and the temperature 1 equals to 25 degree, and the final temperature or T2 equals to 928 degrees Celsius. So need to add 273 to equate the degree into Kelvin, equals to 25 plus 273 equals to 298 Kelvin. Also the temperature 2 plus 273 equals to 928 plus 273 equals to 1001 Kelvin. So need to use the formula of Gay-Lussac law. So the unknown here is pressure 2. Formula is P1 over T1 equals to P2 over T2. So pressure 1, the value is 2.03 atm over temperature 1, 298 Kelvin, equals to unknown P2 over the temperature 2 is 1201 Kelvin. So calculate 2.03 over 298 equals x over 1201. So the value of the pressure 2 equals to 8.18 atm. So cancel the units. So the final answer, P pressure 2 equals to 8.18 atm.